Welcome to this chapter on AI for pre-construction estimating and scheduling. These early decisions shape the project's cost, time, safety, and overall constructability. Traditionally, pre-construction has depended heavily on the experience of estimators, schedulers, project managers, and trade partners. That professional judgment is still essential. AI does not replace it. Instead, AI can help teams organize large amounts of information, compare alternatives more efficiently, identify risks earlier, and make planning decisions with stronger evidence. The key idea is that better pre-construction planning creates a stronger baseline, and when the baseline is stronger, later project controls become more meaningful. One important use of AI in pre-construction is AI-supported quantity takeoff. Quantity takeoff is the process of measuring drawings or models to determine the materials, labor, and assemblies needed for the project. In traditional practice, estimators often spend many hours manually tracing drawings, reviewing sheets, or extracting quantities from BIM models. AI can improve this process by using computer vision, deep learning, and natural language processing to recognize and measure building elements more quickly. For example, AI tools can identify walls, doors, openings, spaces, and repeated objects in 2D drawings. They can also flag quantity changes when drawing revisions are issued. When AI is connected with BIM, the process becomes even more valuable. BIM provides geometry and object information, while natural language processing can help compare model quantities with written specifications. This can help surface scope gaps that may otherwise be missed. However, AI-generated quantities should never be treated as automatic bid quantities. The estimator still needs to verify the drawing set, revision date, scope assumptions, waste factors, exclusions, trade responsibilities, and construction means and methods items before the numbers are used for pricing. The goal is not to remove the estimator. The goal is to reduce repetitive measurement work so the estimator can focus more attention on scope, risk, constructability, and pricing judgment. AI can also support cost prediction by analyzing historical project data. Traditional estimating often relies on spreadsheets, cost databases, vendor quotes, subcontractor input, and estimator experience. These are still important, but they may not fully capture the many factors that influence final cost, such as labor availability, regional market conditions, material escalation, project complexity, site access, and procurement timing. Machine learning models such as artificial neural networks, support vector machines, and random forests can study past project records and identify cost patterns that may not be obvious through traditional estimating methods. These models can consider variables such as floor area, number of stories, project type, location, material price indices, labor conditions, delivery method, and productivity history. For labor cost, AI can compare historical labor hours with crew size, season, location, material type, and productivity performance. This gives the estimating team a broader evidence base for planning labor needs. AI can also provide early warning signals. When current project data begins to move away from expected patterns, the system can flag possible cost exposure before it becomes difficult to control. But this depends on a strong data foundation. Historical cost prediction only works well when cost codes are standardized and when the organization keeps both the original estimate and the final cost outcome. Without both pieces of information, the company cannot learn from past performance. AI can strengthen cost prediction, but the estimator remains responsible for local market judgment, subcontractor quote validation, scope interpretation, and final pricing decisions. Another major application is AI-based schedule simulation. Traditional construction scheduling is often based on the critical path method, or CPM. CPM remains a very important construction management skill. However, a traditional schedule usually represents one selected plan. It may not fully show the many alternative sequences that could be possible. AI-based schedule simulation expands scheduling from creating one static plan to testing many possible construction sequences. The system can evaluate crew availability, equipment capacity, material lead times, production rates, curing time, site access, inspection requirements, work zones, and spatial conflicts. This approach is often described as generative scheduling or construction optioneering. Instead of asking only, "Can this schedule work?" the project team can ask, "Is there a better schedule under the same constraints?" When AI is connected with BIM, the schedule can also be visualized as a 4D model. This helps the team identify spatial temporal conflicts, such as two trades being scheduled in the same limited area at the same time. AI also helps with rapid resequencing. If weather, labor shortages, equipment limitations, or material delays affect the project, AI can quickly test revised sequences and resource plans. Still, the final schedule must be reviewed by experienced planners, superintendents, trade partners, and project managers. A simulated schedule may look efficient on screen, but it must also be constructible, safe, contractually realistic, and aligned with actual field conditions. AI is especially useful for what-if scenario planning. Construction projects are filled with uncertainty. A project may be affected by late material deliveries, design changes, labor shortages, permitting delays, weather events, or owner-driven changes. In pre-construction, AI allows the team to test these possible disruptions before the project is fully committed to the field. For example, imagine that steel delivery may be delayed by 3 weeks. AI can identify which activities would be affected, estimate the impact on the critical path, calculate possible cost exposure, and compare different recovery options. The value of this process is not that AI removes uncertainty, it does not. The value is that AI helps managers study uncertainty earlier and compare responses before they are forced into reactive crisis management. What-if analysis is also very helpful for owner communication. If an owner asks whether the project can be accelerated by 1 month, the team can compare realistic options rather than giving a simple yes or no answer. AI can help explain the cost, schedule, safety, and coordination trade-offs behind each option. To gain real value from AI in pre-construction, firms need disciplined implementation. First, they need to build a reliable data foundation: historical bids, estimates, schedules, BIM files, procurement records, vendor quotes, production records, and final cost outcomes should be centralized in a common data environment. Cost codes, activity names, work packages, and scope categories should be consistent enough for AI tools to compare past projects with current opportunities. Second, firms should start with focused pilots. It is usually better to begin with one specific problem, such as quantity takeoff speed, conceptual estimating, schedule risk analysis, or procurement lead time forecasting. A 30, 60, or 90-day pilot can help the team compare AI outputs with traditional methods before scaling the tool across the organization. Third, AI tools should be integrated into existing workflows. Estimators, schedulers, and project managers should not have to copy data repeatedly between disconnected systems. AI works best when it connects with estimating software, scheduling platforms, BIM models, procurement systems, and document control platforms. Finally, firms need clear review protocols. Before AI outputs are used in bids, owner presentations, procurement decisions, or baseline schedules, the team should define who reviews the output, what assumptions are checked, what source data was used, and how changes are documented. AI should support construction management decisions, not simply produce more data. This case study focuses on construction optioneering through generative scheduling. In a traditional process, a scheduler prepares one baseline schedule based on experience, milestones, subcontractor input, and known project constraints. That schedule may be reasonable, but it usually represents only one version of the plan. Testing many alternatives manually can be time-consuming, so only a limited number of options are often considered. AI-supported construction optioneering changes this process. Generative scheduling platforms can test many combinations of crew sizes, shift patterns, work sequences, crane arrangements, delivery strategies, and zone breakdowns. The system can then compare trade-offs between time, cost, labor, equipment, and resource conflicts. For example, the project team may compare whether a weekend shift is more effective than adding a second crew, or they may test whether changing the sequence of interior work reduces congestion and protects the critical path. The lesson is not that AI produces the perfect schedule. The lesson is that pre-construction planning becomes stronger when teams can compare multiple options before field work begins. Responsible use still requires experienced human review. The team must confirm that the simulated schedule is constructible, safe, contractually realistic, and aligned with trade partner capacity. AI can recommend possible paths, but the construction manager must decide which path is appropriate for the actual project.